Linear motion, two moving objects, d, velocity time graphs. So we know we always end up using velocity time graphs when the object doesn't have constant acceleration during its journey. So in this example here on page 28 in Oliver Murphy's book, we have a passenger train leaves a station. We're told that it starts from rest and moves with a uniform acceleration of 0.5 meters per second squared until it reaches 40 meters per second. It then continues at this speed uniformly, and as it was leaving, a goods train passed it, moving at a constant speed of 24 meters per second on a parallel track in the same direction. We're asked after how long and how far from the station will overtaking occur. And we've to neglect the lengths of the train. It's irrelevant to the question. So because we have the passenger train accelerating and then moving at a uniform velocity, let's sketch what it would look like. So we can see P for passenger train. So it accelerates, so it's going to be an increasing straight line. And then when it reaches 40 meters per second, we can see that it travels at a constant speed of 40 meters per second. So we will draw a horizontal straight line. Whereas with the goods train, it is constantly moving at a constant speed, so it is not accelerating at all. Therefore, we have a horizontal line passing through 24. Okay, so how long is it accelerating for? Well, let me break this down. Well, we know that it starts from rest and has a uniform acceleration of 0.5 meters per second squared. So that's the acceleration. And we know that the velocity reached is 40. So let's break that down into stage 1 and stage 2 of the journey. And therefore what we can say is that in stage 1, it reaches a velocity of 40, an acceleration of 0.5. So we have V and we have A, and therefore T we can work out. So A is equal to V over T. Therefore T is equal to V, which is 40, divided by the acceleration, which is 0.5. And therefore it is accelerating for the first 80 seconds of the journey. So we can mark that in on our graph. As you can see, I've already done that. So we have 80 for the first stage of the journey. And therefore, whatever time overtaking occurs, let's say it occurs after t seconds, then for the second stage of the journey, the time taken must be t minus 80. Okay, so we know that when overtaking occurs, because they're starting from the same position, that S1 must equal S2. So that's going to be the key to solving this question. So how do we work out S1 and S2? Well, when it comes to the graphs, when we're working out our distance travelled, it is equal to the area under the curve. So for S1, our passenger train, we know that the area under the curve is going to equal to the triangle plus the rectangle. And the base of the triangle we've worked out is 80 and the height is 40. The base of the rectangle is going to be t minus 80 and the height is 40. So to get the distance travelled, we get the area of a triangle, which is half the base by the perpendicular height. And we get the area of the rectangle, which is length by width. So in other words, we say S1 is equal to 1,600 plus 40t minus 3,200. So S1 is equal to 40t minus 1,600. So if we do the same for the goods train, Well, the goods train is travelling at a uniform speed. So if we go back, the shape is just a rectangle with base t and height 24. So in other words, the distance travelled by the goods train is going to be represented by the area of the rectangle, which is length by width. In other words, just 24t. So we say on overtaking, these distances must be equal. So we equate 40t minus 1600 is equal to 24t, and therefore we have 16t equals 1600, and therefore the time for the journey for them to overtake is 100 seconds. So in other words, overtaking occurs after 100 seconds. And if I then sub t into either S1 or S2, it doesn't matter. I'll go with S2. Then we have S is equal to 24 times 100. So S is equal to 2,400 meters. So what does that mean? Well, it means overtaking occurs (2,400 meters from the start). So from the station after 100 seconds. So our second example here is taken from Rowntree, where we have a cyclist travelling at 8 meters per second, observes a car just beginning to accelerate uniformly from rest 40 meters distant. If the cyclist's speed remains constant, he can just catch the car. So we have to show the motion of the cyclist and the car on the same speed time graph. We have to find the acceleration of the car. And if the cyclist had been travelling at a steady speed of 6 meters per second, how near would he have got to the car? So our graph then, cyclist horizontal line because it's got a uniform speed and no acceleration, and the car is accelerating uniformly. So therefore it is a linear increasing, a straight line that is increasing. Okay, so what information do we know? We have to find the acceleration of the car. Well, if we do a sketch, what we have is a gap to begin with. So we have the cyclist. And then we have the car. And the car is 40 meters ahead of the cyclist. So if I say that's S1, and that's S2, and that's D, then we know S1 is equal to S2 plus D on overtaking. So if we look at the area travelled, we know that S is equal to our distance, which would be equal to the area under the curve. So if I look at S1, the cyclist, then we can say the cyclist has the shape of a rectangle where we don't know what the time is, but we do know it has a velocity of 8. So therefore the distance travelled is length by width, so 8t. And for the car, we know that S2 is equal to the shape of a triangle with base t and height 8. So in other words, S2 is equal to half the base by the perpendicular height. So S2 is equal to 4t. So in other words, we're looking at this point here where their velocities are the same, because this is the point where they will just catch the car. So therefore, if we put that into our information about our D, so we say, but D is equal to S1 plus S2. Sorry, D is equal to S1 minus S2, I should say. Then I know D is 40, and we have 8t minus 4t gives me 4t is equal to 40. So in other words, t is equal to 10 seconds. So therefore that allows me to work out my acceleration, because I know from my triangle that I have t and I have 8 and I have a. But of course t we've worked out is 10. And therefore I can say A is equal to V over T. So therefore A must be equal to 8 divided by 10. So the acceleration of the car is 0.8 meters per second squared. So for part 3 then says, if the cyclist had been travelling at a steady speed of 6, how near would he have gotten to the car? So we draw a new graph for this. And how close would he have gotten to the car is looking for the greatest lead there. So we have our car is still got the same acceleration, but the cyclist has now got a steady speed of 6. So this shaded area here will represent the greatest lead. And we don't know at what time that happens. We do know that the acceleration is 0.8 for the car. So we know that this shaded area is equal to the closest they can get. Okay, so the area of that shaded region, if we look, it's a triangle. It's a right angle triangle. That's 0.8. We've gone up 6 and we don't know the time, so that's going to be t. So therefore we can say that this is our velocity. In red. That's our velocity. That's our acceleration. So we know that the acceleration is equal to velocity over time. Therefore, time is equal to the velocity, which is 6, divided by 0.8, which means that this gap is going to occur at 7.5 seconds. So, of course, we need to know, well, what is that gap? So, therefore, our distance is always the area. And the area of that triangle is half the base by the perpendicular height. So that's going to be 3t. So therefore the distance travelled at the time, 7.5 seconds, is 22.5 meters. But we have to remember that there was already a gap of 40 meters. So therefore, how near would he have gotten to the car? Is going to be 40 minus 22.5, which is 17.5 meters behind the car. So you're going to do question 14 on page 31 in Murphy. And then on the sheet that I've attached, you're going to do 46, 47 and 48. Okay.